Infinite series to lay the groundwork for sequences, and we're going to kind of start from the beginning here. So if I'm talking about a series, I can talk about how a series converges. And so in this lesson, we're going to understand what it means to say a series converges. We're going to understand the properties of an infinite series, meaning that it repeats forever, and we're going to be able to use the nth term test for divergence of an infinite series. So an infinite series is a series where we're adding values forever. So there's no end point to the series. Sometimes we will refer to this as just a series, but the appropriate terminology is an infinite series. In this infinite series, the numbers a1, a2, and a3 are considered the terms of the series. And for some series, it will converge, which seems weird, right? If we add an infinite number of things together, we're actually going to get a number answer. So when that does converge, it means we're adding incremental numbers that are very small, and that's why over time it will converge. So as a typesetting convention, it's common to represent this as the sum, which is the epsilon symbol there, of a sub n. So that way we're not having to write out all those terms that we're consistently adding together. In cases like this, the starting value for the index must be taken into account. So if I were starting at 1 or 0 or 2, that's an important thing to note. If we want to find the sum, then we have to consider what we call the partial sums. So meaning, what is my first term? What's the sum of the first and second term? What's the sum of the first three terms? Because if I can look at those patterns and see if those numbers aren't changing very much, I can probably start to determine if it's converged. So if I'm seeing a pattern there, like something like 4.1, 4.11, 4.1111, I can start to say, okay, I think this is actually going to be approaching a specific number. So to look at this for the nth partial sum, so obviously I don't want to add the partial sums up to, say, 100. That would be a waste of my time. We can start to look at this and use a limit to explain this. So limits are really the foundation building blocks of calculus. And so if I can say the limit s is the sum of the series, if the sum diverges, then the series itself diverges. So if I'm looking at those little pieces that I'm adding up and they aren't converging to anything, then what I can do is use that logic to reverse back and say, well, the series doesn't actually converge to anything. So an example of this would be the series of 1 over 2 to the n. So first of all, if we just think about this from a limit perspective, the denominator is going to grow really, really fast. And so if I'm looking at the limit, I know it's going to approach 0 as I start to look at it. So that's just an important thing to note here. So if I look at the partial sums, I start noticing that I have a half, and that there's a considerable jump from a half to 3/4, but not so much of a jump from 3/4 to 7/8. And so because I know that infinite sum series, 2 to the n minus 1 over 2 to the n, because I know that is going to converge, then I can then turn around and say, okay, the series is going to converge, and it's going to converge to 1. If I look at this one, and I look at the series of partial sums, I can basically describe them as 1 minus 1 over n plus 1. So that's the partial sum equation. If I look at that, then I'm going to say, well, that's going to converge to 1, because if I take the limit, that 1 over n plus 1, the limit of that is going to become 0. So then if I do that and I take the limit, I just have 1 minus 0, which is going to be 1. Another example is this one. If I look at the limit of this, my partial sums would just be n. So like the first partial sum is 1. The second one is 1 plus 1 or 2. So if I take the limit of n, that's going to be infinite, so it's going to diverge. So when we're talking about convergence and divergence, it's looking for a numeric limit versus a infinite limit. This is an example of a telescoping series. It's a specific name. And it's interesting because if you look at that term B2, it's canceled out if I remove those parentheses. And so I have some really interesting behavior there because of it. And so the nth partial sum of this series is going to be that first term and then the next term, because the middles are going to cancel out. So if I look at this and I take the limit as n approaches infinity, then I'm going to see that if the series converges, then the sum would be this statement: the limit of b sub 1 is b sub 1 minus the limit as n approaches infinity of that bn plus 1. So in this case, this series will only converge if b sub n approaches n number. So b sub n plus 1 has to have a limit that's a number. If it doesn't, then it's not going to converge, and that's something that's a bit unique. Geometric series are something you probably haven't seen in a while unless you're teaching pre-calculus. And this, a geometric series, is going to be a fraction, typically, or a number that's being multiplied by something to generate the terms. So if I look at 1/2, to get from 1/2 to 1/4, I'm multiplying by 1/2. So that's where the 1/2 to the n comes from. If we remember from our geometric sequences, if the ratio is less than 1, then it converges. If the ratio is greater than 1, then it diverges, and that would be the absolute value of those ratios. The same thing applies to a series. So if I'm looking at the convergence of a geometric series, that would just be the statement of the rule that I just gave. If the absolute value of the ratio is greater than or equal to 1, then that's the case. So here's an example. I have a ratio. The ratio is what is being raised to the n here. So my ratio is going to be 1/2. It doesn't matter that my starting term is 3, because the absolute value of the ratio is less than 1 and greater than 0, so therefore it converges. And I can use the formula for a geometric series, which you might want to copy down, which is a over 1 minus r, where a is going to be the initial value that's being multiplied. In this example of a geometric series, it has a ratio of 3/2. Since 3/2 is greater than 1, right off the bat, I can say, well, this diverges. So that's the nice thing about those ratio tests. Here's a couple of examples of geometric sequences and how we can break them up to be able to apply the information to them. The last one that's a nice simplistic thing is the nth term test for divergence. So this is kind of like geometric series, where there's a simplistic rule we can apply, and it will make our lives a lot easier. So in the nth term test, we say if the terms themselves converge to 0, then the series will converge. So that's it. If I just look at the sequence itself, and if the sequence of terms that I'm adding together approaches 0, then the series will also converge. If the limit is not 0, then it diverges. So really simple application there. So if we look at part A, if I have 2 to the n, and I take the limit of 2 to the n, that is infinity. So that means that it's going to diverge because it's not 0. If I look at n factorial over 2n factorial plus 1, then that means that if I take the limit as n approaches infinity, I'm going to have basically even powers at the top and the bottom, so it's going to be 1/2. Now, sometimes people want to say, oh, well, the nth term limit is 1/2, and that's a number, so it's going to converge. But that's not the case. The nth term test says that it has to converge to 0, and that means that since this does not converge to 0, then the series itself diverges. So an example of one that is going to converge would be 1 over n, and as I look at 1 over n, that limit does approach 0. And so in this case, the nth term test tells me that the series of 1 over n, starting with n minus 1, does converge because that nth test. So a lot of times I prefer to use the nth term test as my first step in testing for divergence. And if that yields something that's inconclusive, then I'll take it a bit further. But this is usually the first stop for me.